So we were talking about functions last time. Find once again about something called a difference quotient. So for a function f of x, this is f of x plus h minus f of x all over h. We said this was the slope of the line connecting 2 points on a function at input values x and x plus h respectively. We also saw something called the average rate of change. And that was actually f of b minus f of a over b minus a. And we discovered these are actually the same thing. Just different notation. So if you label the points differently, you might get one versus the other. But usually when you hear something mentioned called average rate of change, they usually refer to this version, because for this version you want to know the difference between the two x values, whereas for this version you only need the particular values for the x values. It saves you a step, and so we might like that one. And nothing much to talk about there. Just like I said, in calculus you'll actually take this and kind of run with it, and you'll get like half of calculus using that expression. That's why it's a very important expression for us to know. But in pre-calc, the examples are just going to be straight up. I'm going to give you a function, ask you to compute the difference quotient as I did on test 1. Or I can ask you find the average rate of change of some function on some interval. So this is on the interval AB. So I can say, silly example, find so that could be a question. Find the average rate of change of that function on that interval. And all you have to do is just plug that into this. So nothing much to talk about here. So here you're going to note, you don't have to write this down necessarily, but note here your A is always going to be the left end point. So your A is -1. And your B is 2, which is the right end point. And so now you're able to say the average rate of change is going to be equal to f of 2 minus f of -1 over 2 minus -1. That's it. And we're going to just plug in each of these one at a time. That's all over 3. So, what is f of 2? How do we find f of 2? Plug in 2 for x. Right? Remember how we looked at functions? The x is just like a location of a void that you can drop anything in. First, we want to drop in 2, and so we get 2 squared plus 4. Secondly, we want to drop in -1, -1 squared plus 4. So that is of course going to be 4 plus 4. And this is going to be 1 plus 4. Notice the parentheses. Kevin knows what I'm talking about. I was in the tutoring center, just like solving problems left and right. Like, you always get something wrong because of parentheses. So it happens. Look out for them. This would be 8 minus 5 all over 3. And the answer is going to be, well, 1. So basically this is saying, on average on this interval, this function, every time the x value increases by 1 unit, the y value will also increase by 1 unit. If it were, say, -1, the way you could interpret that is to say every time x increases by 1 unit, the y would decrease by 1 unit. So picture here, of course, x squared plus 4. You go from -1, you would end up at 5. And if you go to 2, you would end up at 8. And basically, we just found the slope of the line here. So rise over run was actually 1. Notice that as we move 3 units over, we move 3 units up. So for every 1 unit that the x increases, the y also increased by 1 unit. So that was the interpretation. Interpretations aside, because that's more Calc 1 stuff, this is just how you do the problem. It won't really be any more complicated than that. I'm going to give you a function, I'm going to tell you the interval, find the average derivative change, and you do this, what I just did. What else do I want to talk about? Piecewise functions. These are functions where the rule changes based on the region of the domain being considered. We've seen many examples of piecewise functions. Probably the most famous piecewise function is the absolute value of x function. You understand that that was a piecewise function because if our x was positive, it gave us something different from 0 versus negative. So the rule that you apply will change based on the region of the domain that you're looking at. So that's the notation. So whenever you see f of x equals, and you see something like this, and they're basically going to list the, say, the rule 1 and region 1, and rule 2, region 2, etc. And they can go up to n things. So they'll just tell you, here's the rule in this region, here's the rule in that region, etc. So those are piecewise functions. Other than that, they kind of pretty much behave just like a regular function does. So let's just actually jump into some examples. Find f of -3, B, find f of 7, C, find f of 10, D, find f of 8. And 2, graph f. I find f of minus 3 if f can be this thing?
Use the first one.
Huh?
Use the first function because it's true. Like 1 plus -3.
Alright, oh. So, first you notice here that that tells you your x is minus 3. So basically you're going to look for what region makes this true. In which region is this the case? You would notice that for minus 3 would fall into this region. Minus 3 is not greater than 7 but less than 9. It's also not greater than 9. It only falls. It is a number that is less than 7. This means that you take that definition and that definition only. I've seen students tell me the outputs of a piecewise function is several numbers, like they write down a list. Well, it could be if I plug a minus 3 here or here or there. This is incorrect. Remember our rules for functions. A function is a rule that for each input it assigns one output. So you cannot plug it in all of them at the same time. You're only plugging in one at the same time, at a time. I've also seen people like they plug it into everything and then add all the numbers together. That's not how they work. Pretty much you notice where your x value is, figure out what region makes that x value lives in, and you only take the definition for that x value. So here, this means that f of at minus 3, our function is taking on this definition, and now we know what that means. It means the x gets replaced by minus 3. And so that's actually minus 2 would be the answer. B. What is f of 7? We call this undefined. So the function is not defined at 7. I know what it is when it's less than 7, when it's greater than 7, but at 7, I don't know. Don't make up some number if it's not defined for you. Okay, so that undefined would be the answer to this one. It's not defined. So that's how we call it. So that is a technical term, I guess you'd say. C. So there are times in math where we call something like undefined versus does not exist versus blah blah blah. Does not exist is not really the right terminology we would use here. We use undefined. F of 10. Plug in the last one. So I'm going to figure out, well, 10 would be here, 10 is not here. 10 is something that's greater than 9. I'm going to take this definition. So 1 minus 10 squared. It's going to be 1 minus 100. Minus 99. And f of 8, well, f of 8 just falls in here. So what is f of 8? It's just 3, right? So when there's nothing to actually plug in, there are no x's to plug in, that means the function is a constant function. It's always going to be 3. So whatever I plugged in that region, any number I plugged in between 7 and 9, not including 7 but including 9 will give me 3. So f of 8.5 is also 3, f of 7.1 is also 3, etc. They'll all be 3. How do you graph a piecewise function? Here's what I would do. 1, you want to figure out the endpoints. And 2, graph that rule in the ordered region. 3, I would say optional. When you get good at these, you can do it all on one pair of axes, but optionally, you can together on one. Axes. But sometimes you don't have to graph them separately. However, to graph them, you do want to find where the endpoints. You do want to know where they're starting and ending. So let's do problem 3, the optional way of doing this. So the optional way is I'm going to graph each of these separately. Some people like splitting it up just so, because if they try to do everything all at once, they get confused. That's fine. Just make sure you know how to graph things quickly and you graph them individually. So 1 plus x, you should know that that's a straight line positive slope passing through y value 1. 3, you should know that that's a horizontal line passing through 3. 1 minus x squared, you should know that that's a parabola. Move reflected upside down, I'll talk about that in a little bit. Shifted up 1, this 1, minus 1, 1. So that's the optional thing. Step 3, you grab them separately. Now, if we go through 1 and 2, which is what we would want to do anyway, we have to figure out the endpoints. So the first thing we're going to do is we're going to realize that 1 plus x does not always apply. It applies for lower than 7. I can think of 7 as an endpoint. So I'm going to find a 7, and I know that that's the endpoint. It will not go further than that. And more specifically, it will be an open hole here, which means I want everything less than 7, so the part of the graph I care about is this part. That's going to go into the main picture. For 3, again, I would find the endpoints. Well, I can find 7 and I can find 9. And so this would look like that, and this would look like that. The 7 cannot be equal to 7, so I'm going to leave that hollow. This one can be equal to 9, so I can shade that in. And I want everything in between these two. So that is going to be a part of the graph. The endpoint for this would be 8. So you should know that. Because when you start to plot them on the same pair of axes, you're going to want to know how they relate to each other positionally. This one applies for 9 or bigger. So 9 is actually going to give me something down here, not drawn to scale, obviously. Here's the 9. And I cannot be equal, so that's going to be a circle. And anything bigger, so it just keeps going. So that's the part of the graph that I want to do. And basically you draw them on the same axes. Of course, you ignore the white parts of the graph, you draw all the pink parts on the same, in their relative positions. But you could also do this all at once on one graph, so I can redo this here. I think it's nicer to move the vertical axis a little bit over. So we have, let's say, 7, 9, and bigger than 9. So what you can do is imagine that the definition splits space into 3 regions. So on the left region, there's one definition, namely this definition. In the middle region, there's another definition, namely this definition. And on the right region, there's this one. And what you can do is you can figure out the endpoints. When x is 7 in the first one, that gives me 8. So I know that it was not equal to 8. So it's like open circle. That's an 8. So that's the first thing I would draw. And then I know that it's a straight line with y-intercept 1. I could literally either just copy this picture here if I did it before, or I can just do it on the spot if I just realize, okay, it's going to be that, it's going to go all the way up to that point. Everything to the left, I know that that's a straight line with y-intercept 1. So that is going to be that part of the graph. Now I know in the middle, I just want y equals 3. So 3 is going to be here. I'm going to draw that horizontal line. And the left is unshaded, the right is shaded. So finding the endpoints can tell me how these two are both located with respect to each other, as well as the extent to which my graphs are going. And finally, on 9, if I were to plug in 9 here, this is going to be all the way at like minus 80. So that's going to be an open circle, and that's going to look like a parabola. So that's slightly curved. So that would be what the picture of this function looks like. So you can draw 3 separate pictures and just know, okay, I'm drawing this picture over here, I'm drawing this picture right here, I'm drawing this picture right here. But you can also do it on the spot, as long as what you want to do is find the endpoints first, and you know what kind of shape you should be drawing until you hit those endpoints. So, might seem like a strange graph to you, but a function like this isn't that strange actually. We're going to look at them again in calculus, and it will. This is an example of a function which we will call discontinuous, and it's going to be important to recognize when you have continuous versus discontinuous functions. Meaning this one is discontinuous at 2 different x values. Let us continue. That's it. That's piecewise functions. Just they work just like functions, except you use a different definition in different locations. That's pretty much it. All the graphing rules still apply. All the ways you plug in a number and evaluate the function still apply, etc. It's just depending on where you are, you might use a different definition. About piecewise functions. Another thing to very quickly go over, because things like this, you know, I've been beaten to death over the head with them. Transformations of graphs. So you should know. We don't put these into practice as often as you would think, but it's important to know. Every now and then you might need to actually know this. You should know the effect of certain effect on the graph of a function when certain arithmetical operations are done to its formula. So let's talk about some transformations. For example, you could graph this with purely your knowledge of transformations, but then again, if you were to graph that, I'd probably just do it the way I showed you before anyway. Well, technically, to graph that, you should probably know what that looks like by heart, because that's just something you would have graphed thousands of times before if you're doing this math thing, right? So, the transformations you want to know. Let's say you have, so f of x is a given function. If you take the negative of f, you should know what that would do. If you just put a negative sign in front of the entire formula, how does that affect the graph? Versus if you put a negative, if you replace all x values with negatives. What does this one do? Huh? No.
Is this an example of a function?
Yes, but what happens to the graph?
It's like, what is it?
Right, it's called reflected. Reflected where? Over x-axis. This one here is reflected over the y-axis. So this one, for example, if you have y equals x squared, it's going to look like that, passing through the origin. Whereas if you just put a negative sign in front of the whole thing, it'll actually flip this over the x-axis, flip it upside down. And you can talk about reflected over the y-axis, so a nice picture to do that, I guess. Well, it will actually work both ways with the cube. If you look at y equals x cubed, it's like that. If you look at y equals the negative x cubed, replace all x cubed with negative x, it will actually flip it in the y. It will look like this. So these transformations are called the reflections. So these are reflections. But we also have other transformations that we call shifts. You can have the vertical and the horizontal types. So you have f of x and you do something like x minus a constant versus x plus a constant. So here, c greater than 0 is a constant. What does this do to the graph? Yeah? So it's a horizontal shift to the right. This one is a horizontal shift to the left. So this is like if I take y equals x squared versus y equals x minus 1 all squared. The original graph is this, but for this graph it is going to shift 1 unit to the right. So this graph, y equals x squared, if I look at y equals x plus 1 squared, that is going to shift over to the negative 1. So these are the horizontal shifts. We also have the vertical shifts. You take a function, you add a number on the outside, and for simplicity I'm thinking of this number as a positive number, versus if you subtract a number. So this vertically shift up c units. This is a vertical shift down c units. So y equals x squared versus y equals x squared plus 1. Y equals x squared versus y equals x squared versus y equals x squared minus 1. And shift up or down by 1 unit. So this was at 0, this is now at 1. And this is at minus 1. So these are the vertical shifts. So if you negate the outside, you reflect in the x. If you negate the x's, you reflect in the y. If you add something to all x values, you shift to the left. If you subtract something from all x values, you shift to the right. Add something on the outside to all y values, you shift up. Versus subtracting, you shift down. Let's say c is greater than 1. Then you have f of c times x versus f of, call it x divided by c. So multiplying and dividing by something greater than 1 versus c on the outside, or 1 over c on the outside. These guys are called the stretches and shrinks. So this one versus this one versus that one versus that one. So this will shrink horizontally by factor of c. This will stretch horizontally by factor of c. This one is stretch vertically. By factor of c. This is shrink vertically. Now you might notice that the x's kind of, these are all stretches and shrinks. Compression would be a nicer word for it, but I always hear people say shrink. One thing you might notice is that sometimes when you're manipulating the x, things happen to be counterintuitive. So you subtract something, it shifts to the right, where you're normally thinking horizontally. Subtracting means moving to the left. But that's because the subtracting does actually mean you move to the left, but the x itself has to compensate for this shift by moving to the right? So the x, you can think of it as trying to keep the same definition intact. So if you subtract something, the x's will all have to become larger to attain the same values. So they all shift to the right. So with the x's, you kind of tend to do the opposite of what you might think. So subtracting is moving to the right, adding is moving to the left, versus multiplying by something larger than 1 is actually shrinking, while dividing by something larger than 1 is actually stretching. Now, the inspiration for these graphs, the examples will probably be the sine function, but we haven't spoken about that yet, so let's just say for argument's sake, let's say you have some graph that looks like this. We'll talk about what this means later on, just to start introducing it. So say you have sine x, this would be 0. What is that? The x value here.
2 pi.
2 pi. Right. Now, if you say the sine of 2x, so you multiply all x's by 2, it turns out that it's not going to stretch, it's actually going to shrink everything. So the whole graph is now going to happen in pi. Versus here, you have that going up to 2 pi, then this one is actually going to stretch. So y equals sine of x over 2, that's actually going to stretch. Because now what you realize, your x actually has to hit 4 pi before it starts to behave like 2 pi behaved here, right? So your x actually has to get larger to keep the same kind of behavior. So that's actually stretching it. Versus, look at the sine function here. What's the highest value of the sine function? 1. Lowest value is -1. So that's, again, these are all y equals sine x, y equals sine x. And now, if I have y equals 2 sine x, this will actually go higher. So the horizontal here are not changing, but the height is going to be 2 and -2. And This is going to be similar. Y equals sine x versus y equals 1/2 sine x. Going to be vertically smaller. This will go up to 1/2 and minus 1/2. Those are transformations of graphs. I think those are all the transformations that you care about at this point. Another thing you want to know, we can apply several transformations at a time. So for example, we could construct things like a sine kx minus b plus c and apply all kinds of transformations. We're going to learn to graph things like this, by the way. And something like a times x minus h squared plus k. So that's like a parabola, y equals x squared that you shift to the left, stretched by a, and added, shifted up by k, etc. So the goal here, everything applies, as I said before, but follow PEMDAS in applying the transformations. So, what? Leave this?
Yes, leave the graphs.
Say y equals 2 x minus 1 squared plus 3. Do you guys have any trouble? Maybe step 0, most people actually wouldn't think about this step actually. But step 0 would you could actually start with nothing but x. And then you would square it. So you think of just a graph y equals x. Squaring that gives you x squared. But most people actually start by thinking of the first graph as x squared. Start with x squared. Step 2, what you want to do is, well, you have to apply a horizontal shift. So you graph the x minus 1 squared. Step 3. So we already take care of the exponents and the parentheses. Next thing to take care of was the stretching. So this is going to be stretched skinnier, but with a parabola you're not even going to really notice, not drawn to scale. And then step 4. So here, this is the y equals 2 times x minus 1 squared. And then finally you build to y equals 2x minus 1 squared plus 3. You take this graph and shift it up 3 units, so that starts at 3. So the final product ends up looking like that. So this is at 1, 3. But as I said, I think very few people would actually go through this process to actually sketch something. It's much nicer and more efficient to actually do it the previous way. Especially if it's not even given to you in this form. If this was an expanded form, to complete the square and then go through this process to get to the graph, I think it's longer than to just do what we've been doing before. But pretty much apply the transformations in the PEMDAS way and we'll get what we want. That's not. Now one more idea with functions I want to talk about before moving on to more computational stuff. So we'll deal with new kinds of functions pretty soon, but in terms of what you need to know about functions in general, that would apply to all the sections all the time. The last thing I want you to know about is the idea of the inverse function. What's an inverse function? Suppose f is a function. A is the set that I'm calling its domain. Usually for us it's going to be the real numbers, not always. And B is the codomain. So a function is a rule. It's going to take every single person here and connect them to exactly one person over there. So that's a function. Its inverse, if it exists, it doesn't always exist. We'll talk about when it exists. Is another function. G of x such that. So, if you have a function, it has an inverse if there's some other function you can find that pretty much goes in the opposite direction. Its domain is B and its codomain is A. And it undoes the f. Meaning, here's a set A, here's a set B. If I have some guy here, x, my f is going to take x and connect it to someone in B, which we normally call f of x. The inverse, if a function exists, for every such value, it will take that guy as input and bring it back to the original x. That will be g. If you have a function that always does that, we call that function the inverse of f. So it is a function such that if I were to take g up, the output of f, it will give me the original input for all x in the domain of f. This is called an inverse function. It's a function that undoes whatever you just did. But sometimes you want to reverse what we just did. Want to note something? First of all, the notation, which ends up being confusing in a lot of contexts to a lot of people, but this is the notation that we kind of keep for historical reasons. in this case, we denote G by this symbol. F, we put a little -1 power. Now, of course, the confusion comes because normally, from the laws of exponents, we think of -1 power as 1 over, but that's not what it means in this context. But that's how we call it. There are cases, and I'll talk about this especially when we get to trig functions, where we actually change the notation from the -1 notation, because it can be super annoying. So I want you to notice that if I say f inverse of x, it is not the same as me saying 1 over f. Not the same. It's a very important thing that not enough people know. One of my Calc 2 students, I wrote tan inverse on a problem, and they thought I meant 1 over tangent. I'm like, no, I would have written cotangent if that's what I meant. I would write 10 to the -1. So that's just a notation. It doesn't mean 1 over. It's confusing, I'm sure, but in theory, someone should have told you that in algebra or pre-calc class, so it's kind of expected. So now I told you, now you know, if you didn't know before. So whenever you put that -1 on a function notation, so yeah, you see x to the -1, yes, think of it like that. But you see a function's name to the -1, it means inverse. It does not mean 1 over. And the inverse might not be 1 over, it could be 1 over, but it's not always 1 over. So that's just a notation. Another thing I want you to note, if f is the inverse, I could have said it either way, but so this still works. I really meant to say g here, but it's not going to matter. Inverse of g, then g is the inverse of f. The relationship is always going to be symmetrical. So once you find a function that undoes one, then the original function is going to undo the second one. So we sometimes determine if two functions are inverses of each other by checking that equation I mentioned in both directions. If I take g of f of x, I should get x, and if I take f of g of x, I should get x. And in this case, it's for all x in domain of f. This case is for all x in the domain of g. An important thing to realize is that whenever you see f inverse of f, that just means this, and whenever you see f of f inverse, that just means that. This is kind of weird applying to trig functions, but when we get to trig functions, I'll tell you that, because sometimes this doesn't exactly happen, because you have the idea of reference handles, so your x out here can be different from your x in here. We'll cover that when we get to trig. How to compute one. I want to know how to compute inverses, assuming they exist, and how to actually sketch them. Probably next time I'll tell you when to know an inverse is going to exist, but it's probably not going to be relevant for a while. Pretty much in any situation where you're going to want to use an inverse function, you're going to kind of be told that you should use the inverse, in which case it's kind of assumed it's existing. Probably you'll get to a class like Advanced Calculus 1 or Real Analysis or Abstract Algebra where you have to figure out whether the inverses exist in the first place. But normally, from now, Calc 1, Calc 2, Calc 3, we're going to tell you, oh, use the inverse to do this. You assume it exists and you find it. So, assuming it exists, how do you find it? Correct. Step 1, switch x and y. Step 2, solve for y. And step 3, this is a nice step, label this y as f inverse of x. Switch x and y, solve for y, that's the basic idea. Why? Because the inverse is going to turn the outputs into the inputs. So if f does this, brings it to that, your inverse is going to take the output as the input and go the other way. So the input and output kind of switch roles. All this means computation-wise, you literally switch the positions of x and y, and then you figure out if the x was the new output, what would it have done? And yeah, that's it. We'll talk about graphing after, but let's get through some examples of actually computing inverses. Here I can think of x as my y equals f of x. Okay, so you want to find the inverse of this guy? Here's how to do it. Write for inverse, switch x and y. Implies I'm going to put x in the position where y was, or to put y in the position where x was. And now just solve for y. We know how to solve equations already by now. We're going to isolate the y by adding 7 to both sides. And we can find y by taking the fifth root of both sides. Now this is an odd root, so I don't have to worry about the plus or minus. And that's going to be the guy. So we could say here, our inverse function is the fifth root of x plus 7. That's our inverse function. Questions on that? Similarly, with b, f of x equals 1 over x for inverse of x and y. This means my x is equal to 1 over y. I would solve for the y and get my y equals 1 over x. This means f inverse is actually the original function. This is a function that is its own inverse. You guys do this one. Well, what do I do? Okay, now what? How do I solve for y here? Okay, and?
Bring all the terms that has a y to one side and move everything else to the other side.
So move the 1 over here, move the xy over there.
Factor of y. Divide by plus x on the other side.
So this would mean your f inverse in this case is going to be x minus 1 over x plus 1. Okay, so for fun, suppose I asked you to show that these two are the inverses. So, another example, show that f of x equals 1 plus x over 1 minus x, and g of x equals x minus 1 over x plus 1 are inverses of each other. If you had to show that, so I gave you these two functions and I asked you to show that, or I would ask you to say something like, check whether or not these two functions are inverses of each other. What would you check?
So you find the inverse of f of x and g of x separately, and then they both equal what the opposite. So like, if you found the inverse of f of
Yeah.
x.
So one way, find the inverse of f done above. Then find the inverse. Well, you would find the inverse of f done above. You would show this is g. So you'll see that it will, if you take the inverse of 1, you'll actually compute the other one. And if you find the inverse of g, which would be similar to the above, and you would show this is f, which means you have to simplify and manipulate it so that it looks exactly like the other function. Another way, so that's one way to do it. That's perfectly fine. Any other ideas? So how you'd actually do that, I actually showed you an example of how to do that, but there's another option. Somewhere there. So that's going back to the earlier definition. So basically you want to show that if you were to plug g into f, the result would be x, and if you plug f into g, the result will also be x. So if you show both of those. So, since we haven't done an example like that, let's actually do that one. So f of g of x, what does that look like? What does that mean here? Right, whenever there's an x, I'm going to instead put it with g of x. So in other words, that guy is going to look like 1 plus that thing, x minus 1 over x plus 1, all over 1 minus that thing. Okay. Now I need to show that this is actually going to give me x. How do I simplify that?
Well, 1 can be anything, so you can set it equal to x minus 1 over x plus 1.
1 can't be x minus 1 over x plus 1.
Oh, sorry. X plus 1 over x plus 1.
Okay.
And then you add, because they have common denominators, right? So then it would be x plus 1 plus x minus 1, which would be 2x. And then you do the same thing for the bottom. It would be x.
So find the common denominator, combine them, and guess you simplify. Another way to do that, multiply everything by the LCD over itself. So x plus 1 times 1, that would be x plus 1. X plus 1 times this, the x plus 1's cancel, and you would just be left with x minus 1. And then x plus 1 times that one, you'll be left with x plus 1. X plus 1 times that, and minus x minus 1. And if you did the combined top and bottom keep, change, flip, you'd get that after a couple steps. Here, notice that you would have the 1 minus the 1. And here you would have what? Huh?
The x would come as denominator, the x is
The what?
the x is x.
The x and the x cancel, yes. And what do we have in the denominator? So it's 1 minus a minus 1, so that's just 2. And in the numerator, now the 1's are gone, it's just 2 x's. X, the 2's would cancel, and you just get x. So that works. The other way, now when it comes to functions, you have to check it both ways. There are contexts in which once it works in one direction, it will always work in the other direction. But for functions, this is not true. You always have to check both. So then I have to go and check the g of f of x. This is just like I take the g and I plug in f instead. So I'm going to put the f in the x position. The g was x minus 1 over x plus 1, right? Yes. And the f is 1 plus x over, was it 1 minus x? It was 1 minus x, right? Not x plus 1. Minus 1. Okay. So you'd have that. In this case, the LCD is 1 minus x. Multiply these two. So you would get the denominators here would cancel. Here you would have 1 minus x. Don't forget the parentheses. And multiply this by this. The x minus 1s would cancel. And multiply this by this. 1 minus x. The x's would cancel. In the denominator we would have 2. In the numerator I would have 1 minus 1. X minus a minus x, that gives me 2x. Again, these cancel, and you just get x. And that's how we can show that they are inverses of each other. Because if I plug one into the other in either direction, x is the result. And we'll wrap up. next time we'll look at how to graph inverse functions as well as we're going to polynomial long division. So, this is fun, right? You remember that? Yeah.